Hi everyone, this is Michael Manchiraju for Physics 2211, and this is Lab 3, Black Hole. Here's an introduction to this lab. The purpose of this lab is to find the unknown mass of a simulated black hole, that's part 1, and to predict the motion of the planet and spaceship orbiting this same black hole, that's part 2. Newton's second law will be applied in the computational model. Additionally, Newton's law of universal gravitation will be used. Since this was a simulation and not an experiment, only systematic errors could occur. That's kind of what's to come. A little preview of the results there. So here are the major physics concepts. You have, of course, Newton's second law, which has been a theme throughout this course. F equals ma, and then you have Newton's law of universal gravitation, where F equals the force of gravity, big G is the gravitational constant, and you have mass 1 and mass 2 over r squared. So here's experimental design. We actually did not have an experiment in this lab this time. It was all coding and simulations. So the system is defined as the sun and the black hole in part 1. The initial conditions here are the gravitational constant, mass of the star, the time interval, which is how many seconds are in 1 year. Here are the calculations for the x and y components of velocity. And then you have the experimental design continued. Here are some of the calculations. Again, this was coded in Python using GlowScript. The initial and final momentum using the star's velocity and mass. We also calculated the change in velocity and momentum. It calculates the change in momentum over the change in time, dp over dt, which is also the net force. Calculates the parallel and perpendicular component of force. And the last line is the momentum principle. And this is how you calculate the mass of the black hole. It calculates the magnitude of the distance from the black hole to the star, and it uses the universal law of gravity. Here are some initial conditions for part 2. You have the mass of the black hole, which we calculated in part 1, which we got to be 1.52 e 10 to the 34. We have the constants here, the planet initial conditions, and the spaceship initial conditions. So here are the calculations for part 2. Here we were calculating the force of the black hole on the planet. We were calculating the force of the ship on the planet, calculating the net force on the planet, and we were doing this vice versa for the ship. So these are included in this top few lines, and then vice versa for the ship is included on these bottom few lines. We also applied Newton's second law when updating the velocity and position of the planet. I don't show it here, but in the code it was called making things move. That's what this is for. So here's the discussion. The average mass of the black hole was found to be 1.52 times 10 to the 34 kilograms. There was one big systematic error that concerns the mass of the black hole. Since the average is an estimated value, so it's an average of the mass as the simulation occurred, it is not equivalent to the actual mass. And remember, we used this mass in our calculations for part 2. And since the calculations in part 2 are based in part in the average mass of the black hole found in part 1, the calculations in part 2 could be off by a certain percentage. And here we have the ending questions. So first I'm actually going to start with the what does it mean question. What does it mean? What is the difference between the parallel and perpendicular components of the net force and the rate of change in momentum? Theoretically, they are actually equivalent according to Newton's second law. In this lab, we calculated dp over dt, which is the change in momentum, and inferred what the net force should be based off of the change in momentum. So we actually calculated the change in momentum, but we didn't actually calculate the net force. And that's kind of the distinction that I think the professor wants us to make in the what does it mean question. And now we have the what if question. What if you wanted to orbit the black hole in the spaceship? Through trial and error, we can find the x and y components of the velocity needed to orbit the black hole. And these would be x equals negative 8 times 10 to the 5th power meters per second, and the y component would be 3.2 times 6 times 10 to the 6th power. All right, thank you.